Good morning, students. Our today's topic is Rayleigh method for finding the first eigenvalue. In order to apply this method, we have to select a special class of trial functions. These trial functions are of the form of linear combinations of the form given by summation alpha I psi I s, where I varies from 1 to n. This psi I, these are linearly independent functions, and these alpha i's, these are scalars, and these are real numbers. So we select the functions phi of this type to apply this method. Now, to find the first eigenvalue, we maximize the function inner product of k phi with phi. So firstly, let us simplify this expression, which is inner product of k phi with phi. Now, substituting the value phi in first and second argument, we get inner product of k. Phi is summation I varies from 1 to n alpha I psi I s. In the second argument also, we have substituted the value of function phi, which is summation k varies from 1 to n alpha k into psi k s. Now, taking scalars outside from the first and second argument, from the first argument we have taken scalar outside, so we get summation I varies from 1 to n alpha I. From the second argument, if we take scalars outside, that will become conjugate, but alpha k are real numbers, so we get summation I and k varies from 1 to n alpha I into alpha k into inner product of k psi I with psi k. Now let us use the notation for this inner product. We have denoted inner product of k psi I with psi k as the functions k I k. We have used double suffix here because we are having two suffixes I and k. So this will become inner product of k phi with phi is equal to summation I and k varies from 1 to n alpha I into alpha k into k I k. So this is the value of inner product of k phi with phi. We maximize this function subject to the condition that the square of norm of summation alpha I psi I, that is 1. Simplifying this term, norms means square root of inner product of the function with itself. So this can be written as the inner product of the function summation alpha I psi I with itself. Now again, if we take the scalars outside from the first and second argument, this will become summation alpha I alpha k. Inside we have inner product of psi I with psi k, and that we have denoted by Cik. So this condition becomes summation I and k varies from 1 to n Cik into alpha I into alpha k is equal to 1. Thus we have to maximize the inner product of k phi with phi with subject to this condition. So thus we can see that we were given the extremal problem, which is denoted by 1 by lambda 1 is equal to maximum of inner product of k phi with phi. We are to maximize this subject to this condition that norm of phi is 1. This is a variational problem, and we have changed this problem into a problem of advanced calculus. And here we are having several variables alpha 1, alpha 2, alpha 3 up to alpha n. So in this case we can use Lagrange's multiplier method. In the Lagrange's multiplier method, we are given a function which is to be extremized, and we are given a relation, and with the help of given function and that relation, by using scalars we form new functions, and the scalars are called Lagrange's multipliers, and then we differentiate that new function with respect to our variables, to get the equations. If we simplify them, we get the values of the variables from there. So let us apply Lagrange's multiplier method. In order to apply this method, let us take phi is equal to summation I and k varies from 1 to n, k I k, alpha k minus sigma c I k, alpha k. These are the functions formed with the help of Lagrange's multiplier, which we have taken here sigma. This is called Lagrange's undetermined coefficient or Lagrange's multiplier. Now we have to find the values of alpha i's. To find the values of alpha I, we differentiate this with respect to alpha I partially, where I varies from 1 to n. So if we differentiate this with respect to alpha i's partially, we get the equation summation k varies from 1 to n, k I k, alpha k minus sigma summation c I k, alpha k is equal to 0. Here this I varies from 1 to n. Thus we get a system of equations in the variables alpha 1, alpha 2, alpha 3 and so on up to alpha n. Now for the non-trivial solution of the system formed, the corresponding determinant that should be equal to 0. So you find the determinant of the system which is given by the system of equations number 6. So from there we get, if we put I is equal to 1 and k from 1 to n, we get the coefficients of the first row of the determinant, which are given by k11 minus sigma c11, k12 minus sigma c12 and so on, k1n minus sigma c1n. And if we take I is equal to 2 and k varies from 1 to n, we get the second row of the determinant, which is given by k21 minus sigma c21, k22 minus sigma c22 and so on, k2n minus sigma c2n. And continuing like this, if we put I is equal to n and k varying from 1 to n, we get the last row of the determinant, which is given by kn1 minus sigma cn1, kn2 minus sigma cn2 and so on, knn minus sigma cnn is equal to 0. This determinant, when expanded, that gives us an equation of nth degree in sigma, and that will have n real and non-negative roots. So if we take sigma 1, maximum of these roots, in that case sigma 1 is less than or equal to 1 by lambda 1, and this gives us the good approximation for the eigenvalue lambda. So this is the Rayleigh method to find the first eigenvalue. In a particular case, if the trial functions which we have taken as the function psi I, if those functions are orthonormal in the given interval, in that case these coefficients Cij, they are given by delta ij, means delta ij means Kronecker delta function. If these two suffixes are same, that function becomes 1, and if I and j are different, then this value will become 0. So by using this in the particular case, to make our computations convenient, C11 will be del 11, so that will be 1, C12 will be 0, C1n will be 0. In the same way, all C11, C22, Cnn, these will become 1, and all the other values of Ci's, j, they will become 0. So in that case, this equation is converted into the form k11 minus sigma, k12 and so on, k1n. In continuing like this, the last row of the determinant, that will become kn1, kn2 and so on, knn minus sigma, this determinant equated to 0. So this again gives nth degree polynomial in lambda and will have n real and non-negative roots. So we can take our trial functions psi I as the orthonormal functions to make our calculations convenient. So this completes the Rayleigh-Rist method to solve, to find the first eigenvalue. Thank you.